So I will then resort to the screen. In any case, feel free, you can click on in the web page of the school, you can just click on my lecture, and you'll see exactly the slide that I'm going to use, okay? So if you prefer, you can follow the slides. And yeah, here and there, I will trickle some homework for you. Good, so we don't need this anymore for now. Right, so what are we going to cover? Let me just. All right, so the plan is like we have 3 chapters. And in the first lecture, what I'm going to cover is things related mostly just to perspectives, because if you are trying to discuss unnatural sensible model, it's better that we understand what we are talking about. So the most important thing, maybe the first half an hour or so, will be about perspective. And what do I mean by that? Before I just going to complete the line, I think that maybe some of you don't realize, especially the young guys, but I think that the lectures in that school reflect the fact that in the field of particle physics, we are on a journey to understand nature, to understand the fundamental interactions. And this journey lasts for, if you think about just the conventional way in which we think about particle physics, this journey is lasting for already, maybe, it depends how you define it, maybe like 70 years. And during these 70 years, it was an odyssey where we, many times in the community, kind of change our perspectives. And I think in the last 10 years, again, there's, to some extent, you can call it paradigm shifts, or a possibility of a paradigm shift about how we understand our task, odyssey, to understand the basic law of nature. But if you just start now and you hear the way we are doing it nowadays, it could be very confusing. So I think it's very important to think about perspectives. Also, you are young, and now you're probably in a junction, in a fork, that you need to decide what you're going to do in your academic future. Hopefully, all of you are going to become the next generation of researchers. And the point is that there are many, many things that you can do in particle physics, and I'm not going to lecture to you, or I'm not going to attempt to guide you what to do. But at least I want to try in the first lecture to give you a flavor of how to consider what you do. Okay, some people might choose, if they are experimentalists, they are choosing to work on the FCC-HH, as Tillman was describing. I don't know if he's here. So that's like you take a task which might take you 30 years to build the next machine. And some other people, if we take to the other extreme, might become theorists and just try to understand things like weak gravity conjecture or amplitude. And then also there could be other people that will shift to do precision measurement, try maybe to measure the size of this pen to accuracy of 1 in 20. Okay, that's also formidable task, of course. And each of these paths is a serious commitment. So one maybe need to try to measure and to weigh which direction one choose. And the truth answer, before we even start on this lecture, is that we have no clue, the people here. And also if you go abroad. And this is from one perspective, this is bad. Okay, when I think we were young, we were all just told that we should study supersymmetry. So they are laughing. It means that I'm right. All that we did is doing model binding or understanding collider prediction and tests of supersymmetry. That was it. Nowadays, we are in a fun situation that our community is very diverse. Different people are doing completely different things. But at least you should understand why is that. So this is, when I'm talking about perspective, this is what I mean. OK, good. So now, maybe I'll put it a bit lower. because I'm hearing myself way too loud. Or I can just remove it. No. There's a zoom.
I can ask.
Okay. No. How is it now? It's okay? All right. Hopefully that will work. Okay. So when I'm talking about perspective, I already hinted that we are in particle physics, we are in kind of a paradoxical situation. Okay? And why am I saying that? Because on the one hand, and this is for quite a long time, unfortunately, we have observation that 100% telling us that there is beyond the standard model. There's something that requires extending our understanding of the usual basic law of nature, the elementary particles and forces. So we know that there must be new particles or forces, or both. Okay. So this is guaranteed. That's great if you are interested in finding this. But on the other hand, the other side of this coin is we are having very hard time to give sharp predictions for how to find these new particle or forces that we are guaranteed to have. Okay, I'll give an example of that. And in order to try to cope with this, then we need to add something else. And unfortunately, we don't have something that is like insurance policy. We don't have like a very, very strong physics principle that telling us what will be the next step, or what will be the next energy scale, or what will be the properties of the type of new physics that explain these observations. Okay? We don't have it. And this is kind of new for us. When we were postdocs at Berkeley, we knew that we were expecting to find the Higgs. It was just after the top quark was discovered, and also people predicted fairly precisely what will be the mass of the top quark. And this goes back to the bottom, neutrinos, charm, et cetera, okay? So for many years, we knew always what is the next target. Now, we are not sure what is the next target. So again, we're going back to perspective. So you need to understand what are the implications of taking this path or another path. And for that, this is why I'm going to propose for you two kind of soft principles that will help you to, if you wish, to weigh between the different possibilities to search for new physics. So I'm going to introduce two soft principles. And we are going to use this through the lectures in order to guide the discussion, okay? So all of this is the first lecture. So if you wish, it's a lot of perspective. And the second lecture and I don't know whether it's going to be the second lecture or maybe it's going to start earlier or a bit later. I don't know how to gauge the time. But it's the second lecture. We're actually going to take one of these soft principles, which is naturalness. You already heard about this in Chaba's lecture. And we're going to deviate from that. So deviate from conventional naturalness. And this is what I meant in the title of this set of lectures, Sensible Unnatural Theories. Okay, so this will be theories that are not natural from the conventional point of view, but still you can understand where and how they attempt to predict what we are going to observe or to explain the, if you wish, the deviation from we find. And this is, of course, very broad and abstract. So I will take one example, one class of models which belong to this type of physics, the relaxion. And we're going to analyze it. We'll understand how it addresses the natural problem, the Higgs mass natural problem, in a way which is not conventional. And then we're going to follow through and see the phenomenology. And what is nice is that the phenomenology of this scenario is vastly different than the other phenomenology that we are more familiar with. You can contrast it, for example, with what you heard last week in the lecture by Ichaba about prediction of composite Higgs model or supersymmetry, and also with what you already heard maybe this morning. So that is going to be kind of interesting. And in the third lecture, what we are going to do is we are going to discuss a little bit the experimental implication of this kind of phenomenology of unnatural but sensible theories. And you'll see that it makes contact with quantum sensors or part of the precision frontier. Okay, so this is the plan. Great. So now I can begin. So lecture 1. So let me start again by elaborating a little bit about what do I mean that we are in this paradoxal situation. So we want to start with writing a Lagrangian. Okay, most theories that we think that describe particle physics would be associated with Lagrangian, even though you hear some people are saying that there are theories that cannot be described. But let's assume that we have the standard model Lagrangian. And of course, we have the gauge part of the standard model. We have the matter part. And we have the Higgs part. And then we have where the new physics part come in. And I already told you that we are almost guaranteed by point 1 there that this is non-zero, so this exists. And why we know that it exists, what are the observability evidence that we have for that? So that's for sure you know, right? We have, on the one hand, we have the observation of dark matter. Now I'm coming from Weizmann. I don't know if you know that Moti Milgrom, the one who invented the MOND, modified Neutrino dynamics, is from Weizmann. So that presumably gives alternative to dark matter. But I think more and more now we see when we look at the differential distribution inside the galaxy where MOND should be very successful, we see more and more beginning of evidence that MOND is not successful where it should be the most successful, okay? So to me, more and more it's telling us that maybe the dark matter is the explanation of what happens. So the evidence for dark matter in very large scale, when we look at the early universe, CMB, etc., but also at smaller scale, galactical scale, where again, we should expect that MOND would be perfect. So this is one. The other one is, of course, neutrino masses and mixing, where in the standard model the masses should be 0, and also no mixing, no oscillation, and finally baryogenesis. So regarding baryogenesis, the standard model twice fails in understanding the cosmological excess of baryons because, first of all, there's not enough CP variation in the standard model. Second of all, there's no deviation from a strong first-order phase transition that's required for biogenesis, and this is why we also think that there's beyond the standard model here. All right, so this is all should be part of what I'm writing here in LU. And here comes the frustration, what I call the paradoxalic status, that we can do the exercise and spend 1 hour on each of these anomalies, observational anomaly, but I will just quickly flash 2 of them. So if we look at trying to understand or address the dark matter problem of the standard model, then you probably heard it several times. Then when we look at the energy scale, so the typical mass of the dark matter, then we know that there are theories which are consistent with the fuzzy dark matter, kind of not hard to write, a theory where the mass of the dark matter is 10 to the minus 22 eV, can go all the way to heavier masses, MeV, GeV, and there are even proposals to have Planck mass dark matter, or almost Planck mass. So I can write here M Planck. And if it's black hole, because there's a sleeves now which allow this, then this will be 10 times the solar mass, which is roughly, I wrote it so I don't forget, this is roughly 10 to the 50 eV, okay? So that's crazy how the range of parameter space to cover. And this is what I mean by the paradox or the frustration that you have this huge range. So let's also quickly understand this in the perspective of neutrinos. So I can write one model of neutrino masses, namely the CISO masses, the CISO mechanism. So here's the Lagrangian, which is related to neutrino masses. So I can actually write, I'm assuming that you're familiar with the usual convention of how we write the degrees of freedom in the standard model. So L will be lepton doublets. And let me now add a right-handed neutrino. So this is a standard model singlet. It's a singlet of all the standard model gauge symmetries. And I'm going to add also my Rana mass for the right-handed neutrinos. And now, if you try to see what is the range of the parameters that account for this model, then let's, for example, talk about this Yukawa. Do you know what is the range of parameters that accounts for the masses of the neutrino, that can account for the mass of the neutrino? Let's suppose that we are looking at conventional CISO, okay? So the right-hand neutrino are heavy. What would be the size of the Yukawa, roughly speaking? Okay. Oh, so if the neutrino are right-hand neutrino are very heavy, then indeed the effective neutrino mass is coming through the famous Weinberg operator, right? L transpose L, H, H, and this will be divided by M, okay? And this will be proportional now to second order in the Yukawa, so there will be Yukawa square here. And you can convince yourself that you can have a Yukawa of order 1, assuming that M is of the order of 10 to the 14 GeV also, okay? So this will be a case where the Yukawa between the left hand and the right hand neutrino is order 1, okay? So here, this is Y of order 1. But there's another possibility to write a model of neutrino mass. What is the other possibility?
Just give it a Dirac mass term?
Yeah, so Dirac mass, okay, so that means that we are going to switch off this m, right? So that means I'm going to take m to 0. And then, very roughly, what would be the typical size of the Yukawa in this case? What's the mass of the heaviest neutrino? Do you know? Should I help you? It's roughly 10 to the minus 1 to 10 to the minus 2 eV. So, OK, I'll help you to break the ice. So how do we find this Yukawa? We will just write y h ln. OK? And we know that so we know that y times the expectation value of the Higgs should be roughly 10 to the minus, let's say, 2 eV, just to keep it simple. All right? This is the wave of the Higgs. Let's call it 10 to the 2 GeV. I don't want to be precise here. OK? So from that, we actually find that y is very roughly should be of the order of 10 to the minus, so this is 10 to the 11, so roughly 10 to the minus 13, give or take. Okay? So what's the conclusion from here? Again, same frustration as here. We can find a model where the Yukawa is order 1, and the mass is of order of the GAT scale, or 10 to the 14 GeV, or another model, totally viable. Both of them would explain all that we know about neutrino masses and oscillation, where the mass that I wrote here is just 0, and the Yukawa is of the order of 10 to the minus 13. Okay, so again, huge range of parameter space. And this is only one model of neutrino masses. There are others. So again, it means that despite the fact that we know that there is anomaly, so we know that we need to add something to the standard model. We don't know what it is, and there's a huge range of parameter space. Okay? So we saw this for the dark matter. We saw this for neutrinos. You should believe me that also in biogenesis, you can actually follow similar arguments. And again, it means that it's very hard for us to make a sharp linkage between the anomaly, the observational anomaly, and the BSM scenario that will explain it. Okay? So this is what I call the frustration, or the paradoxic situation. Now, some of our friends sometimes argue very strongly about one particular solution of that. So here I'm in the part of perspective. I warn you, okay? It's very hard to have, without extra ingredient, it's very hard to actually give a very strong argument for one model or another to account for these anomalies, okay? So that's, if you wish, the tragic truth. Great. So now what I want to do is to add two soft principles. In order to help us to distinguish between a model of beyond the standard model, and maybe also, if we're lucky, they will tell us something about which scale of new physics should we expect and how to search for it. Now, from the name, soft principle, you can already guess that it's not going to be a very sharp statement. Unfortunately, I wish we could have a very sharp statement. And I think, again, if you go maybe, so 2022, so if you go maybe 20 years back, you would hear people making very strong statements about how to search for the new physics and how to find it. But I think that now we matured, or actually the physics didn't change, the principle didn't change, so we should have been honest even back then and say that we have a soft principle. It's not something that we can guarantee. And what are the two soft principles that I want to highlight? One, as I already mentioned, is naturalness. Okay? And the second one is related to the quality of theory And this is in the perspective of that it should be UV insensitive. So right here, in parentheses, insensitive to Planck physics. So for now, I want to put this in parentheses because now it's not very useful. It will be more useful a bit later, okay? And first we want to talk about naturalness, but also you'll see in the way I like to think about naturalness, it's also about the idea, and I think that's I'm going to show you basically a copy from the original paper of Tufte, that in both cases, when you think about it, the rationale behind those principles is the following, that we want to be able to, if you wish, to define our microscopic theory in a way that we get a stable or well-defined relation between the microscopic parameters, or the Lagrangian that we define at very short distance, and what we measure now. These are measurements that we do at long distances. So if you wish, it's an abstract way to think about the idea of causality. So we'll go back to that. Now, of course, you heard a lot already about naturalness in the lectures by Chaba. Okay? So I'm not going to cover everything. I looked what he covered at the beginning, and I want to give you one slight difference description of how to think about naturalness and natural and unnatural parameters, because again, I want to push to this idea that it's about having a well-defined relation between the microscopic and macroscopic description of nature, or the nature which we define at short distance and long distance. Why? Because later when we are going to discuss theories of unnatural but sensible, this will be useful for us, because otherwise it gets very confusing. What is sensible and what is not sensible? So to me, it's like the causality, the causal contact, which is important, okay? Not in the sense of special relativity a la Einstein, but in the sense that you can understand well-defined connection between the microscopic way that you define the law of nature and what you measure at low energies or long distances. Okay. So I started when? 11:15, right? Okay, good. So for now, what we are going to focus is naturalness. Actually, I can keep this. I will use it in a second. So for now, I'll keep it here and move here. So what I'm going to focus mostly at the beginning is naturalness versus the Higgs mass. And after we'll talk a little bit about this, we're going to switch to something that I don't think that was mentioned in the school, but correct me otherwise, and I'm going to talk about the cosmological constant. Okay, and that already is going to take us into the first step of going beyond conventional naturalness. All right. So what is the problem? If you will open Wikipedia, you'll find that there's a lot of definition of naturalness. By the way, even the Greek kind of thought about issues which are related to the concept of naturalness. There's also Dirac naturalness. But this is not what we are going to discuss today, because I think that this is not something that can be robustly defined. What I'm going to describe is something which go by Tooth as technical naturalness. And before I define it, I just wanted to tell you, again, by thinking about this several times in several years, I think that, and then going back to read Tooth's paper, I think that he really had a good grasp of what's the problem. The problem is when we go to quantum field theories, okay? When the theory is classical, then we might discuss Dirac naturalness, why parameters in the theory are small, but it doesn't lead to, if you wish, to bold contradiction or totally loss of the relation between the microscopic and macroscopic theories. Why is that? Because when we consider quantum field theories, and I'm assuming that you're all familiar with quantum field theory, then there are two phenomena that are really makes things very, very interesting and give the theory very rich structure that is the part of the QFT. And this is related to the fact that you have basically running of Copley constants. I will just write it as running because I'm assuming that you're all familiar with the formalism. And the other thing is operator mixing. Write it a bit bigger. Now, all the time, I'm going to use this analogy of understanding a theory in the microscopic scale and then trying to predict what happened in the long distance. So it's not the usual notion of causality, but it's very close to that. So all the time, what I want you to have in mind, and it will be useful also when we are going beyond naturalness, is some picture where we have the Lagrangian defined, but because of these two phenomena, this happens when you change the scale of the theory, right? When we integrate degrees of freedom, then we get both that the couplings are not constant and operators that appear in the Lagrangian mix among themselves. So when you have this in mind, it means that it's much less trivial to define your theory, right? Because what happened is that, let's say this is us, so this is low energy. Okay, this is where we do the measurement, and therefore we measure the operators, the coupling, which appear in the Lagrangian at this energy. But by what I defined before, what we want is that if you wish, the law of nature, we want to define them at some microscopic scale, so at, let's say, high energy. And this is complicated because if we look at the various coupling that we write in the theory, okay, let me just call them now generically GI, then let's say that this is energy. So this is high energy. This is where we want to define the theory. So we define the theory by defining a coefficient coupling of several operators. Okay. So here I put 4 dots for 4 values of coupling. And of course, we have much more. The theory is much more rich. We have many operators. What happened when we try to do the measurement? So this is, let's say, this is the UV. And here is the IR. Here is where we do the measurement, and here is where we want to define the microscopic theory. What happened is that when we go to the IR, then first of all, these couplings run, so they change their value. So 1, 2, 3, and here another one. That's the generic picture. Okay, they change very much between their value at the UV and IR. But it's even more complicated because there's operator mixing. So there could be couplings and operators that I set to 0 in the UV. But in the IR, suddenly they appear because they mix with this original operator. And suddenly I get here a much more rich picture of many other couplings. Okay? So a priori, if we don't know anything, then it's very hard to understand what we measure here as a function of how we define the theory in the UV. So you get two options. Either you exactly match it to what you measure here, but then you get maybe very complicated and unnatural understanding of what's happening, and there's no clear way to go and define the theory in the UV like what we want, okay? So the connection, again, is generalized way to think about the causality. So that's the complication. This is why it's a challenge. And the criteria that Hooft coined, technical naturalness, is exactly to separate the theories which have a well-defined relation between the UV and IR, and theories where it's much harder to control, and I want to demonstrate this. And this way to demonstrate it is, for example, thinking about this model. This simple model has everything in order to understand the complexity. So, for example, let me first start in thinking about this coupling, Y, okay? So suppose I want to track, I do a measurement. Suppose I measure neutrino's double beta decay, and I measure, which is 0, and I measure all kind of properties of neutrino masses, and I actually get to the conclusion that I don't have a right-handed neutrino, and the neutrinos are Dirac. So they are controlled by this one coupling here, Y. And this is a measurement that I did at very low energies, okay, neutrino, related to typically to very low energy experiments. And I want to relate it to the high scale. And of course, I can do the same thing if I have right-hand neutrinos a la CISO, and this is very high scale, okay? It doesn't matter. So first of all, I can ask what is the beta function, what is the running of the Yukawa, right, of this coupling. And it's something, okay, maybe I should not guess. So I can write the RG equation, something like dy over d log mu. Goes like basically y times the beta function of the Yukawa, and very roughly the beta function of the Yukawa in this case is y squared over 2 over 16 pi squared. Again, the precise number are not important, but I think that's the right answer. Okay, so mu is the scale of the RG, and that's exactly what allows me to define the Yukawa in some UV scale, and then see what happens to it in the low scale. Okay, so you see this is dy divided by y cubed, y times y squared. So I can solve it, and I get something like YIR squared minus 1 over y UV squared, and this is equal to some log of mu UV over mu IR. And now all I need to do is to invert it to get YIR as a function of y UV and the scale. Okay, that's what we are after in this picture. And what you get is very nice. To first approximation, I will assume that this is small because of this 1 over 16 pi squared, which I forgot. So there should be here 1 over 16 pi squared. So what you get is YIR is equal to YUV times 1 plus a small number, which is y squared divided by 60 pi squared, YUV squared divided by 16 pi squared times the log, sorry. This is why I'm more relaxed that I know that you have the notes, because it's written much more nicely there, times log of mu UV divided by the scale that you want to do the measurement. Something like that, okay? And the reason why it is so nice, if I will assume that y, let's assume that y is much smaller than 16 pi squared, order 1, order half, okay? Then what you see from here is that YIR will be almost the same as YUV. So it's proportional to the UV value of it, times very small correction of the order of log, and the log here can't be too big, even if I define it at Planck scale, few tens at most, times the same small number, order, let's say, if I said half, this will be quarter divided by 16 pi squared. That means that we can now completely change this picture. Okay? And now let me put here y. By the way, in the lecture notes, you can actually see the plot where I honestly calculated it, but it doesn't matter. What you see is that there's a very small, we said that this was roughly half at the UV scale. Let's say this is roughly half. And you see that there's a very, very small change for the running of the Yukawa. And more importantly, you see that the IR value, or any value that we measure, is linearly proportional to YUV. And in this case, the corrections are also YUV squared, but that's less important. Okay? So if Y is small in UV, if it's big, then we might lose perturbativity. So that is fine. It's a free game. It's a fair game. But assuming that it is small, then first of all, it will remain small. And also, there's a very simple relation between the UV and IR, what we wanted to achieve. And now I want to contrast it. I want now to try the same game, but looking at another parameters of this theory, which I didn't write explicitly, but you see there's the Higgs here. I want to add the Higgs mass. So let me add, okay, doesn't matter the sign here. The Higgs mass is just another coupling in my QFT. And I can also ask the same question. What about the RGE evolution of the Higgs mass? Okay? And we'll see whether we get a different picture or not. Fantastic. So I can erase everything related to neutrino. By the way, any questions so far? Okay, good. So now I want to do the same thing, but I want to write the same RG equation, but for this parameter, the mass of the Higgs. Okay, so now there will be mh squared here. So if I begin with the standard model, then it's actually pretty simple. I just write beta m standard model times mh squared. And beta standard model is very roughly, I don't care about the order 1 parameter here, it's of the order of yt squared plus 8 lambda minus 3g squared over, again, 16 pi squared, where the parameters here corresponds to the top Yukawa, the Higgs self-quartic, and the SU2 coupling. So it's quadratic with the coupling, similar to what we saw with the neutrino, in fact. And it's still proportional to the Higgs mass. So if you're not careful, and some of our friends from our community are also, by the way, making wrong statement about this, so stay alert. Remember what I'm telling you now. If you're not careful and you just look at that, you see that, again, this will be proportional to the Higgs mass. So to some extent, if I keep it small compared to the UV scale, then the evolution will be proportional to itself. Okay? So if you're not careful, you would say, okay, there's no difference between the Higgs mass and the Yukawa of the neutrinos that we wrote here. But you'll be wrong in two ways. One is easier to understand, and one is more subtle. Okay? So let me now describe the easier way. The easier way to understand why this is wrong is now let's not only look at the standard model case. Remember, we have neutrino masses, so let's also add these new terms, these two new terms. And in particular, we see interaction between Higgs and the lepton doublet and the right-handed neutrinos. That means that when we evaluate the beta function, we have another contribution to the beta function of the Higgs, right? Because we have a diagram which looks like that. Okay, so this is two-point function of the Higgs, so it will renormalize the Higgs mass. And here I have L and N. Okay, so you see that it's proportional to this coupling square. And now, when I evaluate this, and in fact, I go above the mass of the right-hand neutrinos, then I see that there's, in the evolution, there's another term which enters. And the new term which enters looks like that. So it's plus, I will write it here, 2y. I wrote it capital Y here, sorry, different notation. So 2y squared divided by 16 pi squared times mn squared. So what happened is that the mass of the heavy right-hand neutrinos above the mass of the neutrino replaces the m Higgs squared in that equation. So we see suddenly there's a stark difference. There's sharp difference between the previous case because now we have something which is not proportional to the Higgs mass. So that means that if I will go back to this plot, so again, here I have now the Higgs mass. Then again, I have some evolution, but when I hit the scale of the right-hand and the neutrino mass, then I change the slope, okay? But for now, I want also to write it in the following way. Because we know that at low energy, the Higgs mass is very low, suppose I want to start at UV scale, which is, I don't know, 10 to the 14 GeV, or something, or maybe higher. So that will be, if I want to define dimensionless quantity, I can actually define the Higgs mass divided by that scale. So let me call this mu UV. It doesn't matter what it is. So I'm going to start small, do the RG evolution. And I know it is small because I measure this. Okay, this is the Higgs mass that we measure at low energy, right? At the LHC, the TV. And now, suddenly I hit the right-hand neutrino mass. Now, there are two effects here. First of all, there will be a different slope above the right-hand neutrinos because now it's sum of two terms for the evolution. But there's also, when I do the matching, there's something which is called threshold correction. So this is, I write it as TH. Now, maybe I wouldn't be lazy. Threshold, okay? And the threshold correction is of the order of this jump here. This is of the order of basically mn squared over 16 pi squared times this Yukawa squared. So that is a bit unpleasant, no? First of all, I have two kinds of slopes. And second of all, once I'm passing this, and remember this scale is maybe 10 to the 14 GeV. So this is huge compared to that scale. And this is the amount of jump that I have. Now let's switch to the principle of causality, generalized causality that I was describing before. Remember, I want to define my theory here, right, in the UV. That was our agreement. And then I want to see how it corresponds to what I measure at low energy. Now you see that there's a problem because if I have small correction here, because I have this huge jump, then I could miss the value at the IR, but by the value of this threshold, by order of 10 to the 14 GeV squared divided by one loop. So there's a huge fuzziness. Small correction here will imply huge correction here. In other words, I need to very finely define my RG trajectory in the UV such that I know exactly the threshold correction. So I will exactly shoot down in order to get very low mass. Okay? Now, this is a property of the mass of the Higgs. It's not a property of the Yukawa of the neutrinos. No matter how hard you'll try, you won't see this. It's a very special kind of situation. You can say it differently if you use fancy words, that the Higgs mass is like it's a trash bin. Okay, it's a garbage bin which collects all the contribution from the UV degrees of freedom in its value through the IR. Okay, and now when you think what actually caused this thing is exactly the fact that a la Tuft, the Higgs mass parameter is not a technically natural parameter. So first I want to show you that you believe me that this is not my words, but Tuft, not that it matters, but it's nice to see this. Now let's see if it works. Amazing. So, no.
More than 5 minutes.
All right. But I don't know, though, if it will lead us. Let me see. Maybe you're right. Because it's nice. What did I do? What about if, no, this doesn't work? Guest? Oh, no. Even worse. Okay. But still, I insist. I want you to see. And then you can open the paper yourself. It's not even a paper. Those days, people had, not like us, they had a very high threshold for what the right papers. So he thought that it's not important enough. It's actually put it in a proceeding in a conference. Thank you. Woo! Sorry. That to keep you awake. All right, so this is, yes, this is I guess it's too small. But you can look at the introduction, not at the beginning. So this, at the beginning, you just say, I'm defining a new criteria, technical naturalness. And then you say, the concept of causality requires the microscopic phenomena follow from microscopic equations. And then he talked about analogy from liquids. And then he defined the criteria. Okay? And what is the criteria? The criteria is very simple. Chaba already did it quickly, but I will repeat it. Yes, so let's do it here. It's actually very simple. You can write it in one sentence. So a technical natural parameter when taken to 0 result with an enhanced symmetry. Okay? You saw this, right? You're not surprised by it. So let's start with the Yukawa here of the neutrinos. As you know, if I take this to 0, I get actually a chiral symmetry where I can multiply either L or N by, I can do axial phase transformation, and this operator transform under it. So it means that if I take it to 0, I get enhanced symmetry. In this case, U1 axial, or U1 cross U1, which is broken by this to a single U1. Yes, that is clear? You all saw this? All right. For the Higgs mass, if I take it to 0, then there is no quantum symmetry. Okay? Now, here is the setting. Remember I told you that there's a simple way to see that there's a problem and there's a subtle way to see the problem? So let me already say it now. Classically, when I take the mass to 0 of the Higgs, there is an enhanced symmetry because there's scale invariant. Okay? So you would think that if you think about scale invariance as a fundamental symmetry of nature. If you take the Higgs mass to 0, you actually satisfy the criteria of 't Hooft, okay? Because when the mass is taken to 0, there's enhanced symmetry. And the enhanced symmetry is scale invariant. However, again, you need to be careful because there is we are looking at quantum theory, so there is contribution at the quantum level of scale invariance because this is an interacting theory. So you see we have here Yukawa interaction, so the Higgs is interacting. And therefore, even when you take it to 0, there's no enhanced symmetry because the scale invariance is broken by the beta function anomaly. In other words, we know that the Higgs must run, so it depends on scale, so there's no scale invariance. That is at the quantum level. In order to see this, you need actually to use the fact that the scale invariance current is broken by the running, and this is not something that you can see through the RG equation because it's perturbative. So this is why people who are not careful, when they look first at this equation, say, oh, then the Higgs mass is technically natural, forget about all your complaint about naturalness. So remember, they're making two mistakes. First of all, they rely on classical symmetry, which is broken at the quantum level. And second of all, it doesn't matter the standard model. We know that there's new physics, and also we know that, for example, there are Landau poles of the hypercharge. So the Higgs is like a trash bin. So this is, if you wish, this is just the phenomena, but it's really the essence of it. This is just the symptom, sorry. The essence of it is coming because of the property of the Higgs mass becoming the junkyard of any degree of freedom that couples to it in the UV. Okay, so this is really the essence of the fine-tuning problem, or the naturalness problem. Great. Now, I want you to remember this because later we'll see an alternative approach to what I was describing now, and we will have to think in this picture to see whether we are solving this problem or not. Okay, so remember that. This is why I wanted to repeat this. Excellent. Now, we can go back to, at the beginning I said, okay, we can look at the Lagrangian of the standard model, and we see that we are missing a term. Therefore, we know that there's new physics, but we don't know how to set the scale of the new physics. So there are too many possibilities. So this is why we want to use the first principle, soft principle of naturalness. I will now refer to the lecture by Chaba, because there you saw how conventional solution to the fine-tuning problem or the hierarchy problem deal with this issue. And what they do is so the lecture by Chucky. What you saw there is that conventional naturalness implies basically TV new physics, okay? You need to add new degrees of freedom to render the Higgs mass a technically natural parameters, and then you basically screen away from all of this complication. You don't have this additive contribution anymore. And basically, we only know, it's a bit disappointing, but we only know two ways how to address this. So I'm sure that Chaba was describing this, right? Either supersymmetry or through generalized dimensional transmutation. So I don't know how exactly you call this, but here you have RS, technicolor, composite Higgs, and so on and so forth. So there was a time that we thought that we found another way with extra dimension, but when we realized that they are all actually related to the same kind of class of dimensional transmutation. So only two ways to address this problem conventionally. In parentheses, I would say about the scale anomaly, you can try to embed the Higgs in a CFT in order to render the scale anomaly not anomaly again, anymore, and then protect the Higgs mass. And there's a very nice paper by, I didn't put it on the, I didn't put it here, but a paper by Skiba and Schmalz and Gustavo Tavares Marquez, I think, that show that even if you try to do this, it still requires adding TeV new physics. So in this box of conventional naturalness, what we know, there is a scale. So we should be grateful, right? We wanted a scale. We found a scale, TeV new physics, if we want roughly to address this. Now, this is soft. Whether it's 2 TeV or 1 TeV or 100 GeV, you cannot guarantee, okay? And unfortunately for the LHC, or Tillman was describing the FCCHH, there's a huge difference. If it's 1 TeV, then great. If it's 2 TeV, depends on the type of new physics, it's already impossible to find it, okay? In some class of models called neutral naturalness. So for the experimentalists, 1 TeV or 2 TeV is like a huge difference. But if you think about this in general perspective, who cares if I screen this threshold correction from 10 to the 14 GeV with putting 1 TeV or 2 TeV or 3 TeV new physics, right? It's a very small difference. Despite the fact that many people are taking fanatically the idea that it should be less than 2 TeV, or less than 1 TeV, or less than 400 GeV. But if you think about the big hierarchy, all the way from the GATT scale or from the Planck scale, then it's not a big deal. And this is why I call it soft principle, okay? We cannot guarantee that it will appear at 2.1 TeV. No, we cannot do this. This is just a general property of the thickness of a scalar mass. Good. So that is when we talk about Higgs physics, okay? Naturalness and the Higgs mass. But if you look at the Standard Model, then there's an unpleasant surprise awaiting for us. Because there's another problem which is much more severe. And this is related to the cosmological constant. Was Jay describing CC? I don't know. No. All right, I don't have time to open a whole chapter on cosmology, but I will just say the few words. So in the Standard Model, as you know, we have another mass parameter. One is the Standard Model Higgs mass. So if we look at the massive parameters of the Standard Model, Lm, Sm, then we have the Higgs mass that we discussed a lot. But then, and this is dimension 2, but then we have another parameter in the Standard Model, the cosmological constant. I will call it lambda, or maybe lambda CC. And lambda is basically dimension 4, energy dimension 4. And if you think about the way that Csaba introduced the hierarchy problem, we just looked at a loop which gives divergent contribution to the Higgs mass. So for the Higgs mass, what we looked is, let's say, loop like that gave contribution proportional to the cutoff of the theory square. For the CC, basically, it's just a loop like that because it's correcting the vacuum of the theory. After all, if you think about it classically, this is just where the overall shift of the minimum of the potential, okay? It's just a constant. And therefore, because every term in the Lagrangian should be dimension 4, we see that the cosmological constant will be subject to the cutoff to the 4th power. Not only that it's even more sensitive to UV. All this threshold that I showed you before, Before, the requirement was that the threshold is coming from a particle which coupled to the Higgs. But to gravity, everything couples to gravity. So this loop will include the threshold of all particles exist in nature. And while the Higgs mass was 100 GeV squared, the value of the cosmological constant is, and I will write it in units of M Planck because that may be the fundamental scale, is 10 to the minus 120 M Planck to the 4. Oops, sorry. So it is of the order of today, if we measure it, and we measure it because it leads to the expansion of the universe, to the accelerated expansion of the universe, this is roughly 10 to the minus 12 eV to the 4th. So 120 order of magnitude smaller than M Planck to the 4th. So if I want to repeat this kind of approach that was described by Chaba, it means that to screen the cosmological constant from all of this threshold, I need to introduce new physics scale at the scale of roughly 10 to the minus 3 eV, sub-eV new physics. And it needs to couple to everything in order to cancel this. So that is a huge toll. And in fact, this is considered by many as the hardest problem in basic physics, not even in particle physics, because it's also cosmology. Okay? I don't think that there's any good solution for that problem in terms of conventional naturalness. This is how hard this problem is. So while last week you spent a lot of lectures trying to solve this problem, suddenly now we see that there's another problem which is much, much, much worse. And we don't know what is the solution for that within the conventional approach. So let's do the first unconventional discussion. How am I in time? 16 more minutes. Oh, okay, fantastic. So this will be our first. When we start, okay, you'll tell me. Yeah, tell me 5 minutes before. Okay, great. So now what I wanted to do is to talk about unconventional solution, and this is came in a paper by 98 by Weinberg. All right. It's commonly denoted as Weinberg's anthropic solution. To the CC problem. So the solution goes like that. When we look at our universe at large, there are maybe 3 things which come to mind that jumping. So, and I will say what they are. One is the universe is big. Big relative to what? Relative to the Planck scale, okay? Because that's the only fundamental scale that I'm allowed to consider when I think about the CC problem. So I can write the horizon psi L universe divided by L Planck, and I see that this is a huge number. In fact, it's a number of the order of 10 to the minus 30 or 10 to the plus 30. If I'm not mistaken. And also the second is that the universe is old. Again, by looking at the time that the universe exists, and we know that this is 10 gigayears, okay, 10 to the 10 years. So this was the length of the universe. This is the time or the age of the universe divided by T Planck. Okay, same thing. It's much, much bigger than 1. And the third thing that Weinberg noticed, and I will say it, I will paraphrase it in my words, the universe is complex. What do I mean by that? It's very rich in terms of structure. It has a lot of structure, a lot of complexities. There are objects which are very small, maybe point-like, like, I don't know, electrons. And there are objects which are very huge, like cluster of galaxies. And in between, we have stars and solar system and what's not, and planets, right? So there are many scales. All of them coexist. And this is not coincidence, because in order to create a lot of structure, it requires time, okay? Because you need a lot of reactions to go through in order to allow for a star to burn, right? You need BBN, you need many elements, you need CMB for the atoms to be created, et cetera, et cetera. So many processes should happen, not to mention biology, right? Needs to go through in order to allow for complexity, for rich structure that will give us so many stuff that we see when we look at the universe. Okay, so what did Weinberg had to say about this? And again, it's not exactly the nature of the paper, but I'm giving you my story of this. So Weinberg looked at something very simple. He looked at the FRW relation for the expanding universe when you put inside radiation, matter, and the cosmological constant. And what he found, that this goes roughly like that. I'm missing an M Planck here. So there's omega radiation, which is divided by roughly z to the fourth. I'm not very careful about 1 plus, we don't care. And then there's omega matter, the mass, which scale like z cubed. And then there's a constant, which is the CC, that doesn't scale with time. Okay? So what happened is that when you look asymptotically at very long time, because of the fact, let's say, that we are living in an expanding universe, we'll get rid of the radiation very quickly, we'll get rid of the mass, and at the end, the only thing that will survive is the cosmological constant. So very roughly, asymptotically, I can just ignore these two and just solve this equation. Okay, h squared is just, okay, so this is what I'm getting here is h, which is a dot over a. I'm sure that you heard it in the lecture by Jay. So this is a square root of lambda. Square root of lambda over m Planck, right? M Planck squared. Okay, so of course I can solve it, dA over A. I put the time on the other side, and I get just A go exponentially like lambda. So it means that there's a typical time scale, or also distance scale, doesn't matter, associated with lambda. So roughly speaking, after time, which is of the order of square root of lambda in the units of m Planck, then everything else will decouple, everything else will be basically expanding to 0, totally diluted, and then we'll have a universe which is just controlled by accelerated expansion of lambda. If lambda is positive, if lambda is negative, what happened after this time scale? Yes, you did the right. So there is a crunch, okay? all the universe, instead of expanding forever, will crunch. So Weinberg actually realized that we are living on a clock that is set by lambda. And if we wait time which is bigger than square root of lambda, then that's it. The universe is just controlled by accelerated expansion or by a crunch. So we have this limited time, okay, compared to that, time for the order of square root of lambda, for something to be created. If we want complexity, if we want richness, it better be that this lambda will be smaller than this time. Okay? Now it goes, so this is the heuristic argument, which I think is amazing. Now it depends on what your taste. You can say, okay, I want to create galaxies, I want to create the CMB, I want to create stars. You'll get slightly different time here, but very roughly you can say that if you want the universe to live for 10 gigayears, then maybe I'll write it, then you'll get an upper bound on lambda, which is very, very strict. What's that? Yeah, 1 second, I will just write it. So very, very roughly, T needs to be, if you want T to be, so how do I write it? Wait, I found a nice way to write it. Yes, so T lambda is very roughly, if you wish, 10 gigayears times square root of T divided by lambda cc in units of M Planck. Okay, so if lambda is small, and the unit should be different. Wait, it should be fourth root of lambda. What did I do here? Okay, I just put the number, so 10 to the minus 12, sorry, my bad. This is just the value of cc. So 10 to the minus 12 ev to the fourth divided by lambda square root, okay? You want to make the universe live long? Make lambda small. You'll make lambda big, it will take control and destroy everything, okay? This is the solution. This is the result of Weinberg. I'll tell you if it's a solution or not in a second. But first a question, yes?
What happens if lambda is negative? You have imaginary numbers there?
If lambda is negative, you should actually change the...
in the root square.
Yeah, no, I understand. Then you need to be more careful, because I assume that it's radiation dominated. But what you'll see is that the universe will crunch if you do it carefully, okay? You just reverse the sign. Any other question about that? Okay, good. So we go back to Weinberg. And what we find is that if we require a galaxy, if we require any structure to allow us to ask this question to be here, then the only option is to make the cosmological constant very, very small. Okay, smaller by 100, 10 to the 100 or 10 to 120 compared to the Planck scale, which is crazy, okay? Is it a solution or not? It depends. It depends on things which are related to stuff that we are going to discuss next time, okay? So let's see if there are any other questions. If not, I will summarize what we saw today. But you see that already this is open door to something which was not described by Chapa, right? Because this is completely different kind of arguments. Whether it's valid or not, we can discuss it. But you see there's something else about it. It's not about adding new physics that will cancel loops or divergences. Okay, so any other question? All right, so what did I describe in this lecture? First of all, I started with just saying that we are living in a kind of a paradoxalic situation that require understanding some perspective. From one hand, we know that there's beyond the standard model because we know that there's observational anomalies required by the observation of neutrino mass and oscillation, biogenesis, and dark matter. But when we try actually to translate this to Lagrangian, we see that we get vast parameter space and vast range of scales to account for that. So it's not sufficient. We cannot actually pinpoint for the nature of beyond the standard model. So in despair, And this is really in despair. We would prefer not to be in that situation. We prefer just to use observation and then prediction, like we used to have before we discovered the Higgs, because then we have the rho parameter, the LEP result, all kind of the masses, etc., the W and Z masses. So we knew where to find the Higgs. Now we don't have this. So in desperation, we are using now two principles, soft principle. We touched only on one of them. That was naturalness. And we saw that it's required that we'll have a simple relation between the microscopic and macroscopic physics. And the naive approach to that was that we need TV new physics. And we were happy. But then we noticed that there's another unnatural parameter in the standard model, and that's the cosmological constant. And that was really a bummer because we realized that we are far, far away from solving this. This is a problem of 10 to the 120. So all the attempts to solve this using conventional approach failed. Maybe your generation will find a solution, I don't know. But the approach that we have currently, they don't work. And then there was this observation of Weinberg, basically that the cosmological constant is something that washing out any information, any structure, the ability to create observers like us. And in fact, when you translate this, you see that it corresponds to very strong bound on the cosmological constants, which is, as you see, very close to the observed value. And what it means and what requires in order to realize this in some theory, then we'll discuss next time. Thank you.
So about the argument that you made for why we expect this 120 order of magnitude correction, I never understand this argument because I don't know how to calculate the vacuum energy QFT.
Right, so again, I would say that you know how to calculate this. What you don't know maybe is to couple it to gravity. But I would say that just use the same principle that I was describing before. If you think about this as just a term that you put in the Lagrangian, then it will obey all the rules of the other coupling in the Lagrangian. This is just a coupling, and all the threshold correction, all the things that I showed for the Higgs will be valid here. And if you think about the fact that gravity couples to not only to, if you wish, the interacting part, but just how much you're away from the zero, because gravity really is sensitive to the energy density and not only just the minimum of the potential, but how much it's away from the zero, then it means that you'll have this sensitivity, okay? That is true. Then you can say things like, okay, but I'm using quantum argument to understand what happens to gravity, and maybe there's a quantum gravity voodoo that we don't know to understand. But again, the approach here, and that's related to the second also principle here that I didn't yet touch, we'll use it later, is that I want to understand simple mind. I want to understand what I measure today without being sensitive to the voodoo of quantum gravity. Okay, if I have sensitivity to what happened there, it means to me that I'm already in the regime which I would not be satisfied, okay? This is, if you wish, hand in hand with the second principle. Maybe there's no other choice and everything related to string theory or whatever, or loop gravity or what's not, that for me will be very, very unsatisfactory, okay? I can give you something that we'll discuss next time even. I'm sure that when Csaba talked to you about SUSY breaking, he talked to you about or maybe not. Did he describe gauge mediation versus gravity mediation, things like that? I see. Okay, so remind me next time, we'll touch a little bit more about that, okay? But for me, this is not going to be satisfactory, and I hope I'll show you more examples. I forgot, but maybe this is for next time, okay. There are a few homeworks, but we didn't yet get to touch it, so we'll get it next time. No, in that case, lambda is just constant. You see, it does not depend on z.
So because in another side, in another age, the bubble parameter is changed in the time. a function of time.
Yeah, because here, if you would be in a universe which asymptotically where these two don't matter, by the way, we are now in exactly this situation, then age is just constant. And it gives rise dA over A, integral dt. This gives just exponential dependence on time. And this continues forever. It's a very boring universe. So no dependence on time. A dot over A is constant.